That's a win.
Move around a bit, you can have it there.
Um, all right. So, my name is Benjamin Pachev. I'm the second speaker of the day to come from Austin, Texas. So, how's it going, y'all? Uh, I'm presenting some joint work with James Trotter here at Simulum. Um, I'll be talking about adding GPU acceleration to FEniCSx with the specific example of the shallow water equations. So, um, the main application that we're looking at is a library of fully implicit solvers for the shallow water equations. It's called FEniCSx. The link is here for people who are interested. It supports a variety of numerical schemes for the shallow water equations, DG, SUPG. We've got a DG-CG scheme, and we're working on more. And the goal of this library is to enable um, model order reduction, adjoint methods, um, all sorts of fun Phoenix-related research with the shallow water solvers. So we're also using it to explore adding GPU acceleration to FEniCSx. Here's an example of the capabilities of this library. Um, what you're seeing is an animation of Hurricane Ike, which was a major hurricane that made landfall in Texas back in 2008. The color represents water height above sea level. So this kind of demonstrates the library's ability to deal with a real mesh, to handle a problem that's actually useful, instead of some toy example. You can see a hurricane approaching landfall, and that red is a massive amounts of flooding and woe. So here's another example, more on the numerical scheme side. This is a dam break problem where you've got a certain amount of water on one side of the dam, a lower amount of water on the other side. At time zero, the dam magically disappears, and you get a shock. So this is a very good test case for the stability of numerical schemes. As you can see, the classical CG scheme utterly fails. And we do have a couple more schemes that we have experimented with, including some hybridized methods that use Joe's work, but they're not on the board. So that's a little bit about SwimNext, so you can kind of have a feel for the applications that we're dealing with. The main objective of this talk, though, is to enable GPU acceleration of common operations within FEniCSx, specifically the assembly of matrices and of vectors. We also want to do this in a way that plays nicely with GPU accelerated linear solvers. For this use case, it's an implicit time stepping method, so most of the time is spent in the linear solver. We need to be able to accelerate that as well. The main objective, though, is to do it in a way that is easy to use, as painless as possible. So this is not the first attempt to do GPU acceleration in FEniCSx. It is built on top of existing work by James Trotter all the way back in 2020. He got a proof of concept working in C++ and was able to accelerate the solution of equations like the Poisson equation and the hyperelasticity equation. There's a paper about this that I encourage you to all go and read. Unfortunately, this work was never brought to completion. And then last year, when I was working on my thesis, I reached out to James and we started working together to continue what he'd done. So this is a very, very simplified version of how assembly currently works in FEniCSx. You have your UFO form. You give it to FFCX. It gives you generated C++ code, which is then called by DolphinX's assembly routines, and it gives you a vector. And if there are any inaccuracies in this, please call me out after the talk. But what we had to do to get this to work with Cuda was to modify FFCX a little bit so that we could call the generated C++ code in Cuda kernels. And the way that was done was very hacky. We basically copy the function and like add a couple wrappers. A lot more work to be done there, but it works. The main work that had to be done was to copy all of the data that's needed for assembly to the GPU. Um, Mesh information, element information, functions, because everything that's done on the GPU has to use a specific dedicated set of memory. And so the assembly routines also had to be completely rewritten in Cuda, and there's a number of different algorithms for doing that. This entailed a lot of modifications to Dolphin X. We attempted to do that in a minimally invasive way um, to maximize the chance of this work actually getting reused. Um, and it's a little bit too involved to completely cover in this talk, but I'm happy to discuss it afterwards. So the contributions I provided were to upgrade James' old code to work with the current develop branch as of February. So it's not compatible with '08 yet. I'm working on that. We added the capability to handle interior fast integrals so that we could do DG methods. There were some bugs that were fixed. And then we added Python bindings. So the this slide, if you don't remember anything else from my talk, this is the slide to remember. The way assembly works in FEniCSx, assuming you have a boundary conditions, a UFO form, you just make your form and then you call assemble matrix. It's really simple, really nice, and that's why I personally love FEniCSx. I love things that are easy. Now, when in dealing with the GPU, we wanted to make this as simple as possible. So we added an extra module called Cuda to have all of the code in the same place. We tried to minimize any changes to the way things work. In Phoenix, you have this Cuda assembler class that manages the GPU um, and all of that. You have to call toDevice on your form, which will copy the mesh and the form, any functions to the GPU. Then you call an assemble matrix method that has essentially the same signature as the classical Phoenix function. And then that returns this CUDA matrix type, which is another custom class, but you can extract a PETSI matrix out of that and then use it in your linear solver or whatever you want to do. A couple notes, if you're doing an implicit method or anything where you need reassembly, you should call toDevice each time you update data on the CPU. And FEniCSx is moving away from PETSI, so we're we're hoping to remove explicit reliance on PETSI in this CUDA edition. But for now, it was easy, so we used that. We only have support for single GPU assembly. That is a work in progress as well. It only supports NVIDIA GPUs. It's another thing we want to work on. And if you're going to use a GPU accelerated linear solver, easiest way to do that is to build PETSI with CUDA support when you are building FEniCSx. So here's some performance results for a couple different benchmarks. And the comparison here is comparing multi-CPU performance to the performance of a single GPU. I believe the GPU we used was a Tesla T4, and then the CPUs were from their AMD EPYC CPUs from the Texas Advanced Computing Center. So this is showing the ratio of GPU to CPU performance. And for assembling a matrix, we're getting a factor of about 10. For assembling a vector, it's around 20. Um, so it's pretty good. Hopefully we can find ways to make it better, but this is kind of the first start. All of these systems have about 100 to 500,000 degrees of freedom, which isn't a lot. I apologize for not having a more involved investigation of the scaling there, but at least we are getting some acceleration. Now, I'm h- linear with the linear solver, things are a lot more tricky for the shallow water equations. We have really nastily conditioned systems, and the PETSI's IOU preconditioner is the only one that I could get to converge, and it's terribly slow. The CPU actually beats it. So I have some work to do to find a good accelerated preconditioner. For some reason, like PETSI's block Jacobi preconditioner scales amazingly, but it won't work for a GPU. So there's some work to do there. And then this is important work because if you don't have a good GPU accelerated linear solver, it simply you will not be useful to use a GPU because most of the time spent in the linear solver. However, if you have an explicit method, you can take my branch of DolphinX and compile it from source, and then you can just pretty much plug and play, and you'll get a 10 to 20 times speed up. So um, take that for what you will. The main goal of this work is to create something that can be used by the rest of you. So we're hoping to figure out a way to merge this back into DolphinX or to contribute to the GPU acceleration work in DolphinX in the future. And then again, multi-GPU assembly support for all non-NVIDIA GPUs. Personally, I'd like to find something that works well for the shallow water equations, a linear solver, but the main goal here is the contribution to FEniCSx. I'd like to thank my collaborators at UT Austin, Mark Loveland, Clint Dawson, and Jennifer Proft, who helped with the development of this SWEMNIX linear solver shallow water solver package. I'd like to acknowledge Eirik Valseth, who has affiliations both with Simula, also the Norwegian University of Life Sciences and UT, and then James Trotter, my co-author on this work. If you're interested in checking out my forks of DolphinX and FFCX, my GitHub username is Pachev. You can also contact me. Um, yeah.
So you're doing like user-facing explicit transfer operations, which isn't what you do for MPI, right? So you know when, because you're going through a Python interface, you know when objects have changed. So why wouldn't you just copy as required objects which have changed? Why do you need to? And the thing is, particularly, we have Grace Hopper coming and various other unified memory cards coming where memory transfer is going to go away because the CPU and the GPU will be on the same memory. So it seems to me like a choice you wouldn't make to make data transfers and user-facing operation, given you've got the massive advantage of being in Python, where you don't have to.
I completely agree with you. This is something we want to add for simplicity, and also a little bit of modeling for simplicity. I made that explicit because I didn't have the time to add that capability, but that is a great feature suggestion.
Did you have a chance to use any of the NVIDIA tools to see what fraction of peak performance you get when you use the 73?
I did not,
Might be a good thing to do, 'cause I think
but
10% freely available to you.
yeah, yeah.
So your matrix solve is the one you're doing. You're probably not in a regime where that solver is advantageous, probably masking your results. So it's really hard to beat the direct solver in 2D on unless your problem is massive. And so you, in order to get into a place where your iterative solves are doing something real and where your comparisons are real, probably need 3D, and you certainly need lots of millions of degrees of freedom to make the measurements mean something.
Yeah, the linear solver is hard, and these the choice of these, this is kind of to showcase the reason for picking these shallow water systems is that the linear forms are the variational forms are pretty complicated, so it was more of a bug testing. If we throw a framework with a Newton solver, will it give me the correct results? And the answer is yes, which means that you can take this and put it into pretty much any Phoenix code, and it should work.
Next speaker will give but AI processors. Johannes from Stimula will tell us a little bit about how to do unstructured amount computations, mathematically filed AI processors.